Welcome back, AP Calc BC students. Mr. Record here, ready to start really a very special video. This is the video that will set the stage for the ending of your Calc BC course, especially as far as infinite series go. This is why we've done all of that work in the preliminary parts of Unit 10 so that it can pay off now. So I want to introduce some very important foundational information and then let that lead us into our first example over topic 1011. We're going to take the quadratic approximation of a function. But first, let's contemplate, think about it here. For nearly 350 years, a lot of mathematicians have really had the power to compute some very ugly functions. And of course, they didn't have their graphing calculators back then. So for example, if you had to figure out what is the sine of 0.2 or the natural log of 1.05 or the fourth root of e, how did people do that long ago? And you might think, well, people probably didn't need to do that. Well, I don't know if I agree with that because there were very, very impressive engineering feats that were done so long ago that really did require a very accurate degree of precision with their calculations. And yet these mathematicians were able to pull that off. Well, the way that they pulled it off is probably very similar to the way that your calculator can do it, because something has got to be able to tell your calculator how to compute the sine of 0.2 or the natural log of 1.05 or the fourth root of e. And so we're going to be studying those same techniques and find out what our founding fathers of mathematics did by pencil and paper. So where are we going to start? Well, if you remember back from topic 4.6 in Calc AB, we learned about this process called the linear approximation. And basically we said that we could take a curve and find a tangent line to that curve at a point, and we could probably use the curve to figure out information, or we could use the tangent line, I should say, to figure out information about the curve. Sure, it wasn't the greatest thing in the world, wasn't the most accurate, but we could pull it off. Now, if you remember a little bit, what we basically did is we used the point slope formula. That's all this is. Y minus some y value at an x of c equal to c is the slope of the function at that c times the quantity x minus that particular x value, which we called c. This is just the point slope formula. If you remember, if you were a student of mine, I like to call the y L of x for linear approximation model. Well, now what we're going to do is basically declare this to be a first degree polynomial in x, right? There's our x, first power. And so I'm not going to call it L of x anymore, and I'm going to call it P sub 1, first degree polynomial. I know the notation looks kind of crazy, and it's like, well, I want y's, I don't want f of x's. Get over it, right? Because that's all that the f of x function is. It's the same as y. If I throw in a c, that just means I'm finding it at a specific location. So what do we know about this first degree polynomial? Well, it has two very important properties. Number one, it matches the function f in value. Let's take a look. What if I go up here and I replace the x with c where it's going to match? I would get P1 of c equal f of c plus f prime of c times c minus c, which is what I have written in blue. But of course, the c minus c is 0, wipes out the f prime. So P1 of c is equal to f of c. That's criteria 1 that has to happen. Basically, it says that the curve and the line touch at the same point. We're going to see some pictures of this in a little bit. I'm going to allude to it right now. There it is. The curve and the point touch. Okay, what else is true? Well, the slope of the function f has to be matching the P1's slope at x equals c. Well, let's check that out. Slope in calculus means derivative, you know that. So if we take the derivative of P1 of x here in red, the derivative of f of c is 0, because f of c is a constant. F prime of c is also a constant. Now be careful, I don't want f double prime of c. f prime of c is a specific constant. It's the slope of f at c. So I drop it down. I'm taking my derivative with respect to x, so this becomes a 1, and therefore I see p prime sub 1 is f prime, evaluated both at c. So we have that fact that the slope is the same. In other words, if I go to my picture, move my ugly face out of the way, I'm saying that the slope of this red line and the slope of the curve right there at that point C are indeed the same. Well, that makes for a pretty good model. I could use that line all day long to figure out the value of the curve at C, but it starts to get a little bit more interesting when we figure out, well, what would we use to approximate the curve away from C? And so that's what gets us to think. And the problem is that the linear approximation doesn't always work so well when the graph has a great deal of curvature. So now we move to the slide and we have to fix that problem. So to do that, we will create, let's say, a quadratic approximating polynomial. Let's add one new term to the linear polynomial. We can denote that one by p sub 2, and it might look like this. P sub 2 of x is beginning stages of our linear model, f of c plus f prime of c, x minus c, all that's what we had before, but I'm going to add a new one. Okay, why am I calling it this fancy thing, a quantity x minus c squared? Well, I want to keep this theme of c alive. We're focusing on being positioned at c, and so by calling this x minus c, it sort of forces my centering to be there. We'll talk more about that later. Of course, I want it squared, and I'm going to put an a in front of it because I don't know if there's a constant in front of it or not. Maybe there isn't, maybe it's 1, but I have to acknowledge the fact that there could be 1 because that certainly affects the curvature. Now notice, we're going to have to find that value of a. All right, well, to determine a and to ensure that this polynomial sub 2 is a good approximation for f near c, let's make sure that p of 2 of x agrees with f in value and slope and concavity. We have 3 things that we want to make sure works. So what that means, P2 has to satisfy these conditions. P2 of C has to equal f of C plus f prime of C, C minus C, plus a C minus C quantity squared, which is f of C. You guys, all I'm doing is I'm saying throw C in for x and see what we got, and you'll see that P2 of C is f of C. Basically, that's ensuring that what's soon to be our quadratic model, which is this green thing, I'm kind of jumping the gun here, is going to touch the blue curve at that point where x is c. And I'm going to make that kind of obvious that this is where c is. Okay, what else has to be true? Well, the derivative of p sub 2, which happens to be, let's take it, 0. Yep. F prime drops down. The derivative of x minus c is 1. When I take the derivative here, 2 in front makes 2a. Yep. X minus c to the first. Yep. And then multiply by the chain rule derivative of x minus c, which is 1. Nothing new. And then if I evaluate this for c, this term disappears. And p prime 2, p sub 2 prime equals f prime. Right there you see it. So that means that the slope of the green curve matches the slope of the blue curve. All right. And that blue curve, remember, is our f of x. It's the thing that we're trying to model. Now, take another derivative. Why not? Let's do it. So if we take the derivative of what we have up here, derivative of 0, 0, derivative of f prime of c is 0, derivative of 2a times x minus c is just 2a. Now, I can't really evaluate this at c because there's nothing to plug in, so p2 double prime of c is 2a. But remember, we also need to know that this must be equivalent to f double prime. So if we set 2a, and I don't have this really written, but I can throw this in, if we set 2a equal to f double prime of c, because that has to be true, the concavity aspect has to match. Then if we solve for a, we get f double prime of c divided by 2. And that's what's going to go here, you guys. And this thing that I'm highlighting is going to be our quadratic model. Now, I know that's a lot of work to develop, and trust me, it's going to get easier. But for right now, this is what we're going to use to start to draw a graph that's quadratic in nature, like this blue curve that you, or this green curve that you can barely see, and we're going to use it to model that original function f of x in blue. I think we're now ready to take a look at our example 1. So our example reads, linear and quadratic approximations for our specific function ln of x. I figured that's a good one to start with. So part A, find the linear approximation to f of x equal ln of x at x equal 1. Well, in order to do this, we're going to start with what we wrote down earlier on in our notes as the P1 of x model. Basically, it's what L of x used to be. It's what y is when you get y by itself in the point slope formula. And it just looks like this. It's f of c. This would be the specific version. F of c plus f prime of c times x minus c. Now, in this particular example, we are going to use the fact that our function is natural log of x. So if I take his derivative, and I can just do that little work here. If I take the derivative, I of course get 1 over x. So what that means I have now here is that my natural log of x, which is I'm trying to approximate, my f of x is approximately going to look like my polynomial degree 1, which is f of c, which is the natural log evaluated at c, plus the derivative of the natural log, 1 over x, evaluated at c, times the quantity x minus c. Okay, well, what do we do next? Well, we want to find this approximation at a very specific place, and that's when this x is 1. Well, the x that I'm talking about is that specific c value. So now I can replace all of the c's with 1. That's my very specific location. So what that means here now is that my natural log is approximately, again, p1 of x, which is natural log of 1 plus 1 over 1 times the quantity x minus 1, which is a fancy way of just saying x minus 1 once everything simplifies. So I'm saying that I could use, I'm going to write this down because I want to complete this. So I'm saying that if I'm trying to figure out a value on ln of x, it's really hard to do, right? Natural log of like 1.3, I don't know that. I could plug 1.3 in for x here, get 0.3, and it's a fairly decent approximation apparently. But I think we can do better. And that's what we're going to do here with the quadratic approximation. So we're going to do the same thing, but we got to build this into polynomial 2. So polynomial 2 of x is going to be, by our definition, and I can swing back to this if we need to see, this is what I have here in this beautiful highlighted green. It would be f of c plus f prime of c, quantity x minus c, plus, and if you remember that value that we just computed, f double prime of c all over 2 x minus c squared. Now all I have to do is compute, I think, another derivative because I don't have him yet, and I think I'm going to use the little space that I have here. F double prime is negative 1 over x squared. And then I'm going to let my c be 1 and put this all together. So I'm also going to reintroduce the fact that natural log of x is approximately equal to this second degree polynomial, which is now going to go by the name f of c, which is natural log of c. I'm going to go ahead and plug in my c value, which is 1 now, to kind of speed things up. So I have natural log of 1 plus the derivative of f, 1 over x, evaluated at 1, times x minus the c, which is 1 to the first, plus the second derivative, which is negative 1 over x squared, all divided by 2, right, because of this guy, and then I have x minus 1 quantity squared. And I think we can clean this up a little bit, and we can say that the natural log of x, once again, is approximately the same as the second degree polynomial, which is, well, what do I have here? I have 0 plus 1 quantity x minus 1, and then I'm going to actually subtract, right, because of the double negative here. And if I multiply by the reciprocal, I believe I get something like 1, negative 1 over 2, right? And this would technically be multiplied by 1. And I think what I did back here, I probably ought to fix really quickly. Apologize for this, but if I go back here, when I found f double prime, I got so excited about the derivative, I forgot to evaluate it at c. This should be a c, which is equal to this 1. No worries, I can easily do a little bit of doctor work there, and that's going to become a 1. Now you can see I have minus 1/2 here that is going to come out in front of x minus 1 squared. So again, to recap, every time that you take these little derivatives, and even the original function, f prime, and f double prime, you're going to plug in the given c, and that's always going to be provided. You'll very rarely, if ever, not know what your c is, and it's probably going to be given to you as an x. All right, so that would be the equation of my second degree polynomial that apparently will look a little bit more like natural log of x. Now, I like part C. It says use these approximations to estimate the value of what is the natural log of, say, 1.05. Well, it won't be too difficult to approximate the natural log of 1.05 using either of these, because we would just simply plug in 1.05 in for our x. So if I do that for polynomial 1, I get 1.05 minus 1, which obviously is 0.05. Now, if I do it for polynomial 2, a little bit tougher, just requires a bit of manipulation via, what do I have here? 1.05 minus 1, right? Minus 1/2 1.05 minus 1 quantity squared. Yeah, this one's a little bit messier because we get 0.05 minus 1/2 times 0.05 to the second power. Now we can throw this in a calculator, and I know that you can do that. It will end up being approximately 0.04875. I'm going to try to take it out to a few decimal places. There are 5 places. Now, how good are these approximations? Well, let's take a look via calculator and see. All right, here we go. I am going to take my graphing calculator, any calculator will work, and I'm going to go ahead and graph the natural log of x. This is the curve that's in blue that we're really trying to replicate. Well, if you remember from our work, I can go in and I'm going to actually now graph our second function. And I think with the calculator, I'm even going to call it P1 to make it match the name. Wouldn't that be cool? And if you remember, that was x minus 1. Now, I want this to have the color scheme to match, so I'm going to change this color just very quickly here back to red. So that's what I would use if I wanted to approximate that curve with a first degree polynomial, which, as you can tell, I'm going to have pretty good results right around in here, but boy, once I get out to here, not so good at all. So let's take a look at our second degree polynomial, which, yep, you guessed it, I'm going to call P2. If you remember, that guy looked a little something like this. It started with a 0. I know, kind of silly. I don't need that. Quantity x minus 1. plus, and then if you remember, it had a 1/2. We'll try to get that 1/2 in there. There we go. And then it was a quantity x minus 1 squared. Now that's going to graph again in this nice little Carolina powder blue. I'm going to change that to, oh, how about green to make it match what I've been doing before. And as you can see, we're getting a better approximation, very likely, over a longer stretch. Now, if you can't really tell, no worries. I can just simply go in and do a little zoom box here. Maybe use that as the upper left corner, right about there. Maybe go to here. And what I will notice here is that if I keep zooming in, I'm going to get a little bit better approximation, perhaps, uh, using one of these curves over the other. And it's actually kind of interesting. It's like, I don't know if my green curve is that much better than my original blue curve. It seems like that red straight line might be a little bit more reasonable. But you're going to find these results are going to vary depending on the function and how many derivatives that we decide to take. Oh, and besides, I messed up. Yeah, I did. You know what? If I go back up to P2, boy, live television here. If I go back up here to my polynomial 2, if I can find it here, there it is. I apologize. This is supposed to be a minus sign. Now if I graph it, I change my mind completely. I think this green curve gives a better approximation than that red line. So once again, apologies for that. This curve right here, I was missing that minus sign. That was intended to be a minus. So by and large, you should get much more accurate depictions of your original curve if you use a higher degree polynomial. Now the moment of truth, if I go one more time here to the calculator and figure out what is the natural log of 1.05, what do I notice? I get 0.04879. Let's return to the document. And I find out 0.04875 was our approximation. I am close to within, what is that? Tens, hundreds, thousands, 10,000s. I am 4/100,000ths away. And all I had to do is use this red equation with the minus sign, no less. So that's how close we are, and that is your introduction to what we are going to call a Taylor polynomial. Anyway, I hope this starts to get you a little bit intrigued about what's to come. We got lots more videos on their way. If you always like what you're seeing, please subscribe, and we'll see you next time.